We are starting Unit 2, and there's part of this that's going to feel familiar because we've been on the edge of talking about some of this. So we are talking about solving a system of equations today, so that is the main topic. And that should be something that you've heard of before, system of equations. So just a little bit of what I'm expecting right here. You definitely should pause this, take out a sheet of paper. You should be writing this down. You should be taking notes like you're in class, solving the problems as we go. That's how you're going to get the most out of this experience. So, lines and slope should be definitely things that you already have a lot that you know about. And we've talked about that relationship between profit, revenue, and cost several times. We've seen those in questions before. And we even talked about this idea of break even. Now, you should be able to say the break even is when we don't make any money. Money we making is the profit, because the amount of money we take in is equal to the amount of money that we have paid. And so here is a really simple revenue and cost function. So thinking about that revenue, money in, maybe we're selling something for $4 each. Cost function, so this is our variable cost here. It's costing us $2 to buy that item. And maybe we had a $50 startup cost of needing to purchase something to make it. And so when we think about the idea of break even, we've talked about this before. And so there's two ways to look at it. So we're going to do this here a little bit graphically. So I hope you've written down these two functions. Pause the video if you haven't. And then I'm going to transition here to Desmos, so we're going to look at this a little bit graphically. So just to get oriented here, actually here, we have the same functions I had on the other screen. I have a revenue function, a cost function, and then the profit is just the revenue minus the cost. And so as we look at these equations, so the cost is right here, 2x plus 50, that's in blue. So notice that here, this initial value, this y-intercept, should be corresponding to the point 0, 50. And so that point right there is on the line. Notice that something about why I know it's on the line is that it makes this equation true. So if x equals 0, and I substitute a 0 here for x, 2 times 0 plus 50 equals 50, which is the y value here that we're saying. So probably one of the first things that should be in your notes is that a point is on the line if it makes its equation true, a true statement. In this case, we get 50 equals 50. So if we think of another point, like at the x value of 10, you should be able to say what the y value here is really quick. 20 plus 50, 70. So the point on the line is 10, comma 70. So when we think about points not on the line, they're going to make the statement false. So if I think about, and I ask the question about 10, 100, so I move this point up here to 10, 100, and I ask you, does that 10, 100 correspond to selling 10 items and the revenue that we would generate? Well, no, because right here we can see that the revenue generated for selling 10 items should be $40. That's this point down here. So if you substitute 10, 100 into this equation, you get the statement 100, right, our y value, equals 4 times 10, 40. 100 equals 40. That's false. So it's false because this point is not on the line. So there we go. There's just a little few comments about deciding if a point is on the line or not. Now, as you're looking at this, I hope that the point that draws your attention is this one right here. So that is the moment, that's a point that is on the revenue function. So there is a point when x is 25, if you substitute 25 right here, the y value is 100. So this point is definitely on the red line. It makes the red line true. But since it's an intersection here, it actually makes the blue line true as well. So 25 is an x value, substitute in here. 2 times 25 plus 50, is that equal to 100? Yes, 100 equals 100, true statement. So this point is on both lines. And notice before, we called that the break-even point. So if we would sell 25 of these items, we will break even. We will have we will have paid for basically all of the items we had to purchase, which is the $2 per 25 items, and then also paid off the initial $50 first fixed cost of buying equipment or whatever that was. Now, if we go ahead and graph the profit equation, which is revenue minus cost, there's a connection here. So that's this green line. Notice that if your profit is negative, like that's a bad thing, that means you haven't paid off your initial cost yet. And so notice that the moment where this crosses the x-axis, that x value is the same as this x value. So, and that's just because that's the profit equation. That's really what we're looking at here. Revenue minus cost. Again, if revenue minus cost equals 0, break even. So this is something that we've seen before, but what we haven't really talked about is how this, the blue and the red together combined, are considered a system of equations. Okay. So with that, you definitely should be able to answer a question like this very quickly. Is this point on either of those lines? Now notice here that I didn't put it in that kind of traditional form of like y equals mx plus b. So sometimes we just have lines. I can see it's a line though because they both have powers of 1. So take a second, jot this down. Is that point on either of these lines? Pause, decide before you go on. So I hope this is what you've done. You have substituted in this x value into this line, and also its y value, which is what you see here. And then you decide, is this true? So 4 minus 3 is 1. 1 equals negative 4. False. Therefore, this point is not on that line. 4 plus 0 equals 4. That's true. Therefore, it is. Okay. So let's think about how, like more generically, how we could think about solving a system through then a method of graphing and some of the things here that might occur. So let me flip back here to Desmos. So this is a picture of that system. Okay. Now, if you're going to solve this by graphing, you actually just need to graph them. Like you can use your calculator to graph these lines, but you should be able to navigate and find the point here where they're meeting. Now, it's always a good idea to check it, like just to make sure you haven't mistyped it into your calculator. Go back to the very original problem. So when we look at this, it seems to be saying that 1, 2 is a solution to the system. It's a point that makes both of those true at the same time. So if x is 1 and y is 2, is that true? 2 minus 6. 2 minus 6 is negative 4. X is 1, 2, 2 plus 2, it is. So we have found a solution to the system. So we can say the solution is the point 1, 2. So solutions to systems should look like points. Okay. Now I just want to see here in Desmos some of the other things that can happen. So I have here some other lines. So now we have this red line and this green line. Now I hope as you look at this that you wonder if these are parallel. So that's something that we should probably check. Like, you don't want these to be like really close together so that if I zoom out, I have to wonder if they're going to cross or not. So let's go back here and do just a little bit of work and try to decide for this system, is there a solution? Okay, because obviously if they're parallel, there's no moment they cross. So I need just to look at 2x minus 3y equals negative 4, and this 4x equals minus 4 plus 6y. And so this together makes a system. So as we're looking at this, we might want to consider what the slopes are. So maybe we need to do some rearrangement, rewrite this in a form that's a little easier to see. So we could move this to the other side. Oops, move that to the other side of the equal to. Have something like minus 3 divide everything by negative 3. So really the red line here, what we're looking at, if we would put it in the form that we're used to, we would have something like that. Okay. And if we look at that, like this does look like 1 and 1/3. Oops, something's wrong. Negative 3. Sorry, that's 2/3. And then if we think about this slope, then that's up a third, or up to up 1, up 2 over 3. That kind of looks right. So I'm kind of visually trying to see, does that slope kind of match what we see? Just make sure I don't get a sign wrong or something like that, which I almost did. So next one here, so rearranging this. So, we could maybe move the 6y back, move the 4x, do some division. You should be doing this on your paper. Dividing by negative 6. And you'll notice right here that these reduce. So we finish this. So as we look at this system is the same as my original system. We haven't done anything here to change a truth equation. And so we're looking at these two red and green lines here. So this is this one, this one, this one, this one. And so right here we can tell parallel lines. There's no solution here to this system. We give a name to this, like so. When the lines are parallel, we call this an inconsistent system. No solution. Now the lines themselves definitely have points on them, right? There's points here, here, here. There's points that make the red line true. There's also points that make the green line true. It's just that they don't share any of those points. Okay, so that's one of the special things here that can happen when we think about this graphically. There's one more special thing here that can happen. So here is the other special thing. So you'll notice that the blue and the orange line are actually the same line. Now, so that means that if I'm trying to find a point that makes both of them true, there's lots of points that make them both true, right? So let me do this. Let me take this back to my OneNote to draw it so we can have the equations as well. So you should be jotting down this system. So our system is 2x plus y equals 4, and 8 minus 2y. So not only are we going to be able to show here that the slopes are the same, we're actually going to be able to rearrange this and show that the entire equation is the same. Notice right here they have the same y-intercept. So if I rearrange this, bottom one, I get negative 2x. And if I rearrange this one, so I'll move the 8, divide by negative 2, 4 divided by negative 2, that minus 8 divided by, I get the same equation. Same slope, same y-intercept. So we give a name to this. It's called consistent because there is a solution. So it is consistent. But the equations actually depend on each other. And so if you look at it, do you notice that we can get the one equation by kind of doubling the other? Right? If the x's get doubled, like if you put them in the same order, maybe it's easier to see. So if I say 2x plus y equals 4, just rewriting that, if I put, if I rearrange this to get them in the same kind of order, notice we would have this minus 4x, I move that over, minus 2y minus 8. So depending on how I'd rearrange it, you can see here that we actually took the top equation and we really multiplied everything by negative 2 to get the bottom equation, which is why we see the same line, right? Multiplying both sides by negative 2, if you do that to everything, shouldn't change the truth of the statement. So we're going to call it consistent, but we also use the phrase dependent, okay? And so an important element here is that sometimes we'll just say there's an infinite number of solutions. And again, all of this should be in your notes. You've got to be able to refer back to infinite number of solutions. Now, sometimes when I say that people think, well, everything is an answer, every possible point. But if we think about where we started today, is this point, 5, 5, a solution to the system? Well, it's not on either line, right? So when I'm saying that there's an infinite number of points, that's true. It's just that it's every point that has to be on the line. So any point off the line definitely is not a solution. So how do we write that? There's more than one way that you'll see it written. Okay. So sometimes you'll see the set notation. So it's the set of all x comma y such that, and then we'll just put the equation of the line such that y is always negative 4. So what we're really saying there is that if I want to find a point that is a solution, so let's suppose I'm looking for a solution that is 3 comma something. Well, how do I find the matching value for when x is 3? Like I can see 3 on my graph here, so 3 is here. So shouldn't the solution be there? Or that y coordinate, whatever matches it? And if you notice that that's all this is saying, so if I substitute a 3 in here, I get negative 6 plus 4 is minus 2, which is actually what we see on the graph. So really what we're saying is, yes, infinite number of solutions. It's just that the y value should always follow this pattern. Why this pattern? Because it's the line. Now, you might be wondering, could I have written the other line? Well, sure, because they're the same line. So I could have written this statement. I could have written this statement in that spot. even written this statement in that spot because they're all the same line. So you're really just describing the relationship. Sometimes you might see, so that's one way that we see the answer written. Sometimes we might see it this way. So when we're looking for the solution, we might say it's a point, and we might give it like a variable like t. So t comma, well, and so this is really just thinking of that same kind of thing we did here. So when x was 3, what did we do? Well, we substituted in 3, that answer. So if x is t, well, you just substitute in t. So our solution would be t comma negative 2t plus 4. And that's the answer. As long as t is any number, we basically just found a point on the line. So for example, if t is 1/2, okay, so that means that when I'm thinking about my x value graphically here, so here is the value of 1, so here's a half. So if x is a half, how do I figure out what y is? Well, wouldn't I just take the x value and put it on the line, which is really all this is saying. So that is negative 2 times a half, negative 1, plus 4. There's our point. And if we look back at our graph, we can count up, and we get our value here of 3. There's the point. Okay. So, in summary, exactly one ordered pair. If you have one ordered pair where those lines meet, then we call that a consistent, and we'll use this phrase independent. If there's no solution, then it's inconsistent, the lines are parallel. If it's an infinite number of solutions, again, that's consistent. So notice the consistent ones here are when there is an answer. It's dependent because the two lines depend on each other. They're really the same line. And that's what this is saying. And then finally, if it's infinite, we're not saying every point makes it true. It's only points that are on the line are a solution. Okay. So you definitely should be able to get through the first MyMathLab homework assignment. Notice the due date. We have the rest of this period. And we're going to move on to something else tomorrow.